Our universe is stretching itself apart at an ever-increasing speed. This silent expansion is not science fiction, but a startling cosmic reality that defies our basic understanding of physics. Picture the universe as a loaf of raisin bread baking in an oven. The raisins, which are galaxies, are not just moving apart as the bread rises. The dough of space itself is stretching faster and faster. Why is this happening, and what unseen force could possibly be strong enough to overpower gravity itself? By the end of this journey, you will understand the mysterious force shaping the final destiny of everything that exists. We will uncover how astronomers stumbled upon this shocking truth and explore what it means for the ultimate fate of the cosmos, from a cold, dark end to the dramatic possibility of everything being torn apart. What do you believe is driving the cosmos to fly apart? That static and eternal universe was a comforting idea, but it was shattered by a man staring through a telescope in the mountains above Los Angeles. Edwin Hubble's work at the Mount Wilson Observatory revealed a cosmos in motion. He focused not just on the positions of galaxies, but on the very color of their light. By splitting their light into a spectrum, he saw a telltale signature. The light from these distant islands of stars was consistently stretched, shifting its signature colors toward the red. Think of the sound of a passing ambulance siren. As it moves away from you, the sound waves stretch out and the pitch drops. Hubble saw a cosmic version of this Doppler effect. The light from galaxies was stretching, turning redder because those galaxies were racing away from us. The implications were staggering. The most distant galaxies showed the most extreme redshift, meaning they were fleeing the fastest. This relationship became known as Hubble's law, the first solid proof that we live in an expanding universe, not a static one. The entire cosmic fabric was stretching, carrying the galaxies along with it. This was a monumental shift in human thought, but it came with an assumption. Everyone believed that the immense pull of gravity would eventually put the brakes on this grand expansion. The real surprise, a discovery that would take decades to uncover, was that gravity was not winning the fight. The universe's expansion was not slowing down at all. It was getting faster. Gravity, the force that holds our world together, should have been the universe's ultimate brake. After Hubble's monumental discovery, this was the unshakable assumption. Every galaxy exerts a tiny gravitational pull on every other, a collective drag across the cosmos. It seemed inevitable that this mutual attraction would slow the expansion, just as the Earth's gravity slows a ball thrown skyward. The ball rises, its speed steadily decreasing until, for a single moment, it hangs motionless before falling back. For the universe, the question was which scenario would play out. Would the expansion continue forever, gradually slowing to a crawl against an endless, dark future? Or was there enough matter, enough gravity, to eventually halt the flight and reverse it, collapsing all of existence back into a fiery big crunch? This was the defining quest of cosmology for decades. The entire fate of the universe hinged on measuring a single value, the deceleration parameter. To find it, astronomers needed a way to measure cosmic distances with incredible precision. They needed a lighthouse in the dark, a standard candle whose true brightness was known. That perfect beacon turned out to be the violent death of a star, a Type Ia supernova. These stellar explosions are so brilliant and so uniform that by observing how bright they appear from Earth, scientists could calculate their exact distance across the vastness of space. It was with these cosmic bombs as their measuring sticks that two teams set out in the 1990s to finally weigh the universe and measure the grip of gravity. What they found, however, was not a slowdown. It was a silence followed by a shock that would unravel everything we thought we knew. The search for the universe's deceleration became a cosmic treasure hunt. Two rival teams, the Supernova Cosmology project and the High-Z Supernova Search team, were not just looking at nearby stars. They were training the world's most powerful telescopes on the deepest reaches of space, hunting for a specific kind of stellar catastrophe. They needed the perfect cosmic bomb, a Type 1, a supernova. These explosions occur under such precise conditions that they always release the same titanic amount of light. A white dwarf star, the dense corpse of a sun like our own, pulls material from a companion star. Once it steals enough mass to reach a critical threshold, a runaway thermonuclear explosion tears it apart. This consistency is what makes them perfect standard candles. If you know how bright a light bulb truly is, you can calculate how far away it is by how dim it appears. These supernovae were the universe's ultimate light bulbs. By finding them in galaxies billions of light years away, the astronomers were effectively looking billions of years into the past. They could measure the expansion rate of the universe in its youth and compare it to the present day. The process was painstaking, requiring them to scan countless galaxies night after night to catch these brief, brilliant flashes. They meticulously measured the distances and the redshifts, plotting the data point by point. They expected to see the curve of their graph bending, showing the expansion slowing under gravity's relentless pull. The data, however, began to tell a different story, one that defied every expectation. Operating in parallel, the High-Z Supernova Search team was conducting its own deep cosmic census. Their name held a clue to their ambitious goal. High-Z refers to high redshift, a technical term meaning they were focusing on the most distant stellar explosions they could find. They were chasing the faded light of supernova that had blazed into existence when the universe was only half its current age, a light that had been traveling through the void for billions of years before finally reaching their telescopes. By carefully measuring both the distance to these ancient supernova and their redshift, which tells us how much the universe has stretched since the light began its journey, both teams could map the expansion history of the cosmos across billions of years. They were constructing a timeline of the universe's growth. The data from both groups pointed to the same impossible conclusion. The most distant supernova, the oldest ones, were significantly fainter than anyone had predicted. In a universe where gravity was reigning in the expansion, these distant beacons should have appeared brighter. Their unexpected dimness meant they were much farther away than anyone had thought possible. There was only one logical yet unbelievable explanation. The expansion of the universe was not slowing down at all. It was accelerating. The very fabric of space was stretching faster and faster over time. The finding was so radical that the researchers themselves were the most skeptical. They spent months searching for a mistake, for any mundane explanation. Could interstellar dust be dimming the light and tricking them? They checked and rechecked every variable, but the evidence was undeniable. The universe was not just expanding, it was flying apart with ever-increasing speed, as if some unseen hand had pressed down on the cosmic accelerator. The results were published simultaneously in 1998, and the scientific world stood still. Two independent teams, after years of painstaking work, had reached the same earth-shattering conclusion. The universe was not merely expanding, it was accelerating. This was not a simple update, it was a complete overturning of our cosmic understanding. For centuries, humanity had believed in a clockwork universe governed by predictable forces, with gravity as the ultimate master. Now, the data revealed a cosmos where gravity was being overpowered on the largest scales. The discovery was so profound it was compared to learning that the Earth revolved around the Sun. Everything we thought we knew about the cosmos was fundamentally incomplete. The leaders of the teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, would later receive the Nobel Prize in Physics for their work. But the prize recognized more than just a finding. It acknowledged a doorway into a new and deeper mystery. The implications were staggering. For the expansion to be speeding up, something had to be pushing it. This unknown something, a repulsive force woven into the fabric of space itself, was given a name that perfectly captured our ignorance. They called it dark energy. In an instant, our cosmic inventory was rewritten. This mysterious energy now appeared to be the dominant component of the universe, the primary force shaping its ultimate destiny. The question was no longer about how gravity would slow the cosmos, but about what unseen hand was forcing it apart. Dark energy is the dominant force in our universe, yet we cannot see it or touch it. Think of it as a kind of cosmic repulsion, a persistent negative pressure woven into the empty vacuum of space itself. While gravity pulls matter together, dark energy does the opposite, pushing the very fabric of the cosmos apart. This is why its effect becomes more powerful over time. Imagine blowing up a balloon with a few dots on it. As the balloon inflates, the dots move apart. Now imagine the act of inflating the balloon itself gets easier and more forceful the larger it becomes. That is the relentless push of dark energy. Unlike matter, which thins out as the universe expands, the density of dark energy may stay constant. This leads to a profound and counterintuitive result. As the universe grows, creating more volume, the total amount of this repulsive energy actually increases, allowing its influence to overwhelm everything else. We call it dark because it gives off no light and interacts with nothing we can directly detect. Its presence is a ghostly signature, deduced only from its overwhelming gravitational effect on the entire universe. The roots of this bizarre idea, however, were planted decades before its discovery, hidden in the work of the very man who gave us our modern theory of gravity. Ironically, the key to this modern mystery was written into the cosmos nearly a century earlier, when Albert Einstein was crafting his theory of general relativity. His own equations presented him with a profound puzzle. The math clearly indicated that the universe could not be static, that it must be either expanding or contracting. Yet every astronomer of his era assured him the cosmos was eternal and unchanging. Faced with this conflict between his brilliant theory and the accepted observation, Einstein made a choice. He altered his own equations, introducing a new term to precisely counteract the pull of gravity. He called this fudge factor the cosmological constant, a sort of repulsive energy woven into space itself that would hold the universe in a perfect, motionless balance. It was a mathematical fix to preserve a flawed idea of a static cosmos. Years later, when Edwin Hubble proved the universe was indeed expanding, Einstein realized his intervention had been completely unnecessary. He famously dismissed the cosmological constant as his greatest blunder, stripping it from his theory. For decades, it was seen as a curious footnote, a legendary mistake by a genius. But the discovery of the accelerating universe in 1998 transformed that story entirely. The very force Einstein had invented and then discarded was resurrected as the prime explanation for dark energy. That repulsive constant was not a blunder at all, but a prophetic glimpse of a truth he could not yet see. This idea suggests that empty space is not truly empty, that the vacuum itself possesses a fundamental energy that pushes the cosmos apart. This strange link connects the immense scale of galaxies to the ghostly, uncertain world of quantum mechanics, where particles flicker in and out of existence. Einstein's greatest mistake may have been his most profound insight, hidden in plain sight for 70 years. Einstein's cosmological constant offers one elegant explanation, but the quantum realm whispers a far stranger possibility. The very definition of nothing might be wrong. According to quantum field theory, empty space is not a barren void. It is a seething, bubbling foam, a microscopic frenzy of activity. So-called virtual particles spontaneously blink into existence and then annihilate each other almost instantly. We know this is real because we can observe its effects in the laboratory. The Casimir effect, for instance, demonstrates this beautifully. When you place two uncharged metal plates extremely close together in a vacuum, they are gently pushed toward each other. Why? Because the tiny space between the plates restricts which virtual particles can appear, while the vast space outside allows for more. The greater activity on the outside literally pushes the plates together. This proves that the vacuum itself possesses a real, measurable energy. This quantum vacuum energy should act exactly like a cosmological constant, creating a negative pressure that pushes the universe apart. It seems like the perfect, natural explanation for dark energy, but here lies a problem of almost unimaginable scale, a puzzle so profound it humbles our entire understanding of physics. When theorists calculate how much energy this quantum frenzy should contribute, the number they get is astronomically wrong. It is not just a little off. The theoretical value is about 1 with 120 zeros after it times larger than the amount of dark energy we actually observe. To call this a discrepancy is like calling the universe moderately sized. It is the single worst prediction in the entire history of science. This staggering failure tells us one of two things. Either our mathematics for the quantum vacuum is fundamentally incomplete, missing a crucial piece that cancels out almost all of this energy. Or dark energy is not the quantum vacuum at all, but something else entirely, something far more exotic and unknown. Einstein's cosmological constant is not the only game in town. Another possibility is far more dynamic and strange, a concept known as quintessence. Imagine if dark energy were not a fixed feature of empty space, but something that flows and changes like a fifth fundamental force of nature. This is the core idea of quintessence. It proposes a cosmic field that permeates all of reality, similar to the Higgs field that gives particles mass, but with a repulsive anti-gravity effect. The crucial difference is that this field is not constant. Its energy density can evolve, growing stronger or weaker over the eons. This solves a profound cosmic coincidence. Why are we living at the exact moment in the universe's 14 billion-year history when dark energy has just begun to dominate? If dark energy were a true constant, its repulsive force would have been the same in the early universe, potentially preventing galaxies and stars from ever forming. But a quintessence field could have been dormant or insignificant for billions of years, only recently awakening to become the dominant force we observe today. This timing is not a lucky accident, but a natural consequence of a changing field. The implications for the future become even more dramatic. A cosmological constant leads to a steady, unending acceleration, a slow fade into cold darkness. But a dynamic quintessence field could lead to futures that are far more extreme. Some models suggest this field could grow stronger and stronger, its repulsive force increasing without any limit. In such a scenario, the acceleration we see today would be just a gentle prelude. The force would eventually overwhelm not just the pull between galaxies, but the gravity holding individual galaxies together. Stars would be flung from their galactic homes. Then it would overcome the nuclear forces binding solar systems and planets together. Finally, in a final, terrifying crescendo known as the Big Rip, it would grow so powerful that it would tear apart atoms, molecules, and the very fabric of spacetime itself. The entire universe would be shredded into a soup of disconnected fundamental particles. This ultimate fate hinges on whether dark energy is a constant or a dynamic field. The quest to find the answer is now a primary driver of modern astronomy. Next-generation telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to be dark energy detectives. They will map billions of galaxies across cosmic time, searching for the slightest whisper of change in the strength of dark energy. Finding any variation at all would be a monumental discovery, confirming that we live in a universe governed by a dynamic, evolving force, and opening a new chapter in our understanding of cosmic destiny. To measure this silent expansion, we need a precise speedometer for the cosmos. That instrument is the Hubble constant, known as h0, a number that tells us how fast the universe is expanding today. Think of it as the current growth rate of our cosmic fabric. Yet, this seemingly straightforward measurement has become the source of a deep and troubling puzzle. The universe's two most reliable cosmic clocks are ticking at different rates. One clock is built from the faint, cold whisper of the Big Bang itself. Satellites like Planck have mapped the cosmic microwave background, the ancient light from when the universe was just a hot, dense soup of particles. By studying the subtle patterns in this afterglow, scientists can extrapolate forward, calculating what the expansion rate should be today. This method gives us a value based on the infant universe's physics. The other clock is constructed from a cosmic distance ladder, a step-by-step method using stars we can see right now. Astronomers start with pulsating stars called Cepheid variables in our galactic neighborhood. Because their pulse rate is directly tied to their true brightness, they are perfect for calibrating distances to nearby galaxies. Then, they use these calibrated distances to pin down the true brightness of Type I, a supernova in those same galaxies. These supernova, the same standard candles that reveal dark energy, then become the final rung on the ladder, allowing us to measure distances and thus the expansion rate across the vast modern universe. Both methods are incredibly precise, but they stubbornly refuse to agree. The early universe method suggests a slightly slower expansion rate, while the local universe method insists it is faster. This stubborn mismatch is the Hubble tension. It is not a small statistical fluke. It is a persistent discrepancy that has survived years of rechecking and improved observations. This tension is a profound clue. It strongly suggests that our standard model of cosmology, the very recipe for the universe that includes dark energy and dark matter, is incomplete. Perhaps a new, unknown type of subatomic particle, like a strange neutrino, was flowing through the early cosmos. Or maybe dark energy itself is not a simple constant, but has evolved in a way we have not yet accounted for. Whatever the answer, this is not a crisis for science, it is an opportunity. The Hubble tension is a signpost pointing directly toward the next great discovery in physics, a hidden door in our cosmic map waiting to be opened. That same faint static on an old television holds the answer. Tune a radio to a dead channel, and about 1% of that snow is the cosmic microwave background, the oldest light in the universe. This afterglow is a fossil from a time when the cosmos was just 380,000 years old, a mere infant. Before that moment, the universe was a hot, dense fog of particles and light, a plasma so thick that photons could not travel any distance without crashing into an electron. But as the cosmos expanded and cooled, a monumental transition occurred. Electrons were finally captured by protons, forming the first atoms. In that instant, the fog cleared. The light, once trapped, was suddenly set free, streaming across the universe for the very first time. That primordial flash has been traveling for over 13 billion years, stretched and cooled by the expanding universe into a faint microwave whisper that today uniformly bathes the entire sky. This cosmic background is far more than a simple relic. It is a detailed snapshot of the infant cosmos, and its subtle patterns tell a precise story about what the universe is made of. Missions like the Planck satellite have mapped this glow with incredible precision, revealing a sky painted with tiny variations, hotter and colder spots that represent the seeds of all future structure. These minute temperature fluctuations are the blueprints for the cosmic web of galaxies we see today, but they also reveal something deeper, the fundamental geometry of the universe. According to Einstein's theory of general relativity, the total amount of energy and matter in the cosmos dictates its shape. The patterns in the cosmic microwave background show us that the universe is geometrically flat. Think of it like this: if you drew a giant triangle across the cosmos, its angles would add up to exactly 180 degrees, just like on a sheet of paper. This flatness is a cosmic balancing act. It requires a very specific critical density of energy. When scientists added up all the ordinary matter and all the dark matter they could account for, the sum fell dramatically short. A huge portion of the universe's energy budget was missing. The only component that could possibly fill the void and bring the universe into perfect balance was the exact same amount of dark energy that the supernova teams had discovered. Here was the proof, arriving from two completely different directions. The death of ancient stars and the birth of the universe's first light were both whispering the same secret. Dark energy is real, and it shapes the very fabric of our reality. Another echo from the Big Bang helps us measure the silent expansion. Deep within the cosmic microwave background, we find the frozen imprint of sound waves that once traveled through the infant universe. Before atoms formed, the cosmos was a seething, opaque plasma, a superheated soup where particles of light, photons, were tightly coupled to the protons and neutrons, collectively known as baryons. In this dense fluid, gravity would try to pull matter together into clumps, while the intense radiation pressure from the photons would push it back out. This tug-of-war created vast, spherical pressure waves that rippled outward through the primordial fog, much like sound waves moving through air. For hundreds of thousands of years, these acoustic oscillations rang across the cosmos. Then, in an instant, everything changed. When the universe cooled enough for atoms to form, the fog cleared. The photons suddenly flew free, and the rippling waves of plasma instantly froze in place. The largest of these waves was caught at the precise moment of its maximum expansion, like a photograph of a splash at its peak. This event etched a specific, preferred distance into the very fabric of the universe. It left a subtle signature, a tendency for galaxies to form at a certain separation from one another. This frozen wave, this cosmic yardstick, is known as a Baryon acoustic oscillation. It provides a standard ruler of known length, permanently stamped across the sky. Astronomers can see this ruler by creating immense three-dimensional maps of millions of galaxies. Within these maps, they can statistically detect that galaxies are more likely to be separated by this specific scale, about 500 million light-years, than any other distance. The true power of this ruler, however, comes from looking back in time. By observing galaxy distributions at different redshifts, scientists can measure the apparent size of this Baryon acoustic oscillation ruler at different epochs of the universe's history. If the universe's expansion had been steady or slowing, the ruler would appear to stretch in a predictable way, but the measurements reveal something else. The cosmic ruler appears smaller than expected in the distant, early universe. The only explanation is that the fabric of space has stretched more than our models predicted, meaning the expansion has been accelerating over billions of years. This third, independent line of evidence from Baryon acoustic oscillations powerfully confirms the story told by supernova and the cosmic microwave background. It is a fossilized echo that tells us dark energy is not only real, but has been actively shaping the growth of the cosmic web for eons. This cosmic recipe, our best map of reality, is known as the Lambda cold dark matter model. Its name sounds complex, but it simply lists the main ingredients. Lambda is the symbol for Einstein's cosmological constant, representing dark energy. Cold dark matter refers to the slow-moving, invisible matter that shapes galaxies. Together, they form the prevailing model of modern cosmology, a powerful yet humbling picture of what the universe is made of. The pie chart of all existence is shockingly unfamiliar. A dominant 68% of the universe is dark energy, the mysterious force accelerating the expansion. Another 27% is dark matter, the invisible scaffolding that holds galaxies together with its gravity. That leaves a mere 5% for everything else. Every star, every planet, every nebula, and every one of us is made from that tiny sliver of ordinary atomic matter. For all its strangeness, this model is incredibly successful. It explains the subtle patterns in the cosmic microwave background, the vast web of galaxy clusters, and the accelerating expansion revealed by supernova. It is the framework that makes all the disparate pieces of evidence fit together. Yet this triumph of science is built on a profound confession of ignorance. 95% of the universe is made of stuff we cannot see, touch, or directly detect. We only know it is there because of its overwhelming gravitational effects on the 5% we can see. The Lambda CDM model is our current, best guide to the cosmos, a map that has proven stunningly accurate. But most of its territory is still labeled "Here be dragons," a silent acknowledgement of the vast, dark unknowns that await our discovery. So the silent expansion points toward a profoundly lonely end. If dark energy is indeed a constant force, as the cosmological constant suggests, then our cosmos is destined for a fate known as the Big Freeze. This is not a dramatic collapse or a fiery explosion, but a slow, inexorable fade into darkness. The acceleration will continue, relentlessly stretching the fabric of space. One by one, the distant galaxies we see today will begin to vanish. They are not moving away through space, but the space between us is expanding so fast that their light will eventually be unable to cross the growing chasm. Their light will redshift into invisibility, and then they will simply disappear from our observable universe, leaving our local group of galaxies isolated in an ever-growing sea of blackness. But the end of light is just the beginning of the end. Inside the surviving galaxies, the fuel for new stars will slowly run out. Vast clouds of gas and dust, the raw material for stellar birth, will be consumed or become so diffuse they can no longer collapse. The last star will flicker out, leaving behind a cosmic graveyard of cold, dead stellar remnants. Brown dwarfs, white dwarfs, and neutron stars will be all that remain, their faint heat slowly bleeding away into the freezing void. Even the mightiest black holes are not eternal in this scenario. Over time scales so vast they dwarf the current age of the universe, these gravitational monsters will themselves evaporate, releasing their mass as a faint whisper of radiation through a process known as Hawking radiation. The final state is one of maximum entropy, a condition where energy is uniformly spread out and no temperature differences exist anywhere. With no hot spots or cold spots, no usable energy can be extracted. The universe becomes a static, frigid, and utterly dark vacuum where nothing ever happens again. This is the ultimate triumph of the silent expansion, a cold and quiet conclusion dictated by the relentless push of dark energy. But the Big Freeze is not the only possible ending. A far more violent fate could await the cosmos, one driven by a dark energy that grows in strength. This is the scenario of the Big Rip. If dark energy is not a gentle, constant pressure but a force that intensifies over time, like a runaway version of Quintessence, then the universe's expansion would not just continue, it would escalate into a cosmic cataclysm. The repulsive force would grow so powerful that it would eventually overwhelm every single force that holds the universe together. The end would not come with a slow fade, but with a sudden, violent unraveling. First, the immense gravitational glue that binds entire clusters of galaxies together would be overpowered. These vast cities of stars would be flung apart into the void. Next, the individual galaxies themselves would be torn asunder. The Milky Way and all its stars would be scattered like dust in a hurricane. As the acceleration intensifies further, it would breach the gravitational bonds within our own solar system. Planets would be ripped from their orbits around the Sun, sent careening into the endless dark. Stars themselves would be shredded, their immense gravity no match for the ferocious push of space itself. In the final, terrifying moments, the force would reach down to the smallest scales. It would exceed the strength of the electromagnetic force that binds atoms into molecules. Molecules would be torn apart. Then, the very atoms that constitute all matter would be disassembled. Electrons would be ripped from their nuclei. Finally, even the atomic nuclei themselves, held together by the powerful nuclear force, would be blasted into their constituent quarks. In this ultimate dissolution, the very fabric of spacetime could be torn apart. The universe would cease to be a coherent cosmos, becoming instead a thin, expanding mist of disconnected fundamental particles, forever isolated from one another in a meaningless void. While current observations do not support this specific, dramatic ending, the Big Rip remains a stark theoretical possibility. It serves as a powerful reminder that the ultimate destiny of every galaxy, star, planet, and atom hinges entirely on the still unknown nature of dark energy. Its silent, mysterious push holds the final word on whether our universe ends with a whisper or a scream. Yet despite this mountain of evidence, a stubborn question remains. Could dark energy be an illusion? Some of the sharpest minds in cosmology argue that what we are seeing might not be a new force at all, but a flaw in our interpretation of the cosmos. One of the most persistent criticisms strikes at the very heart of the original discovery. Our entire case for acceleration rests on the reliability of Type Ia supernova as perfect standard candles. But are they truly flawless? What if these exploding stars were subtly different in the ancient, younger universe? Perhaps the white dwarfs that exploded billions of years ago had a slightly different chemical composition, causing them to be inherently fainter than their modern counterparts. If that were true, we would mistakenly interpret their dimness as greater distance, fabricating the illusion of an accelerating expansion. Or maybe our maps of interstellar dust are incomplete. If vast, unseen clouds of cosmic soot are dimming the light from these distant supernovae more than we've calculated, it would create the same deceptive signal. Researchers have scrutinized these possibilities for decades, searching for any evolutionary trend in the supernova data or any missing dust. So far, no such systematic error has been found that could explain away the acceleration, but the possibility remains a tiny, open door for doubt. A far more radical idea challenges the very laws of physics themselves. For a century, Einstein's theory of general relativity has been our unshakable guide to gravity, from the orbit of Mercury to the bending of light around galaxies. But what if this brilliant theory, while perfect for our solar system, begins to fray at the edges of the observable universe? the apparent acceleration might not be caused by dark energy, but by our own misunderstanding of how gravity works on the largest imaginable scales. This is the realm of modified gravity theories with names like MUND, which stands for Modified Newtonian Dynamics. These frameworks propose that the rules of gravity change when its pull becomes incredibly weak, as it is in the vast emptiness between galaxy clusters. In this picture, there is no mysterious dark energy. Instead, gravity itself behaves differently over cosmic distances, creating effects that mimic an accelerating expansion. It is an elegant idea, a single adjustment to a fundamental force that could explain both why galaxies spin faster than expected and why the universe seems to be flying apart. The problem, however, is one of harmony. A successful theory of the universe must sing in tune with every instrument in our cosmic orchestra. The Standard Model with dark energy does this remarkably well. It predicts the specific patterns we see in the cosmic microwave background, the precise clustering of galaxies revealed by Baryon acoustic oscillations, and the apparent acceleration from supernova. Most modified gravity theories, by contrast, struggle to hit all these notes at once. They might beautifully explain the rotation of a single galaxy, but then fail to account for the intricate temperature variations in the Big Bang's afterglow. Or they might adjust to fit the supernova data, but in doing so, break our understanding of how galaxy clusters collide. The Lambda CDM model, for all its mysterious ingredients, remains the simplest and most complete symphony that fits all the data. This does not mean the alternatives are wrong. It means that to replace dark energy, a new theory must be even more powerful, more encompassing. It must not only explain the acceleration but also everything else we see, a challenge that keeps physicists searching for a deeper, more unified truth hidden within the silent expansion. This silent expansion is the target of the most ambitious astronomical campaigns ever conceived. The next decade will see our cosmic maps redrawn with stunning clarity by a fleet of new observatories, both on the ground and in space, all designed to hunt the dark universe. Their mission is to answer a single, pivotal question: is the push of dark energy a true constant, or has it been changing all along? In Chile's high desert, the Vera Sea, Rubin Observatory is preparing for an epic 10-year census of the sky called the Legacy Survey of Space and Time. Its massive mirror and gigantic camera will not just see billions of galaxies, it will watch the sky in a motion picture, detecting subtle changes night after night. This torrent of data will allow scientists to track the universe's growth in two powerful ways. It will measure weak gravitational lensing, the way the gravity of dark matter warps the light from distant galaxies, tracing the invisible cosmic web. And it will chart the clustering of galaxies, using the frozen sound waves of Baryon acoustic oscillations as a cosmic ruler across different epochs. Meanwhile, in the vacuum of space, the Nancy Grace Roman Space Telescope will perform its own deep and wide surveys. With a view 100 times larger than the Hubble Space Telescopes, Roman is a dark energy detective built for sheer scale. It will discover thousands of the most distant Type Ia supernova, building a more precise history of the expansion than ever before. Simultaneously, it will peer across billions of light years to measure how dark matter's gravity bends the shapes of galaxies, providing an independent and exquisitely sensitive measure of dark energy's influence. Across the globe, the European Space Agency's Euclid mission is already on its way to a similar goal, creating an immense three-dimensional map of the universe to trace the subtle tug of war between dark matter's pull and dark energy's push. The combined power of these missions lies in their convergence. They are not relying on a single method. They will use supernova, Baryon acoustic oscillations, and weak lensing all at once, cross-checking the results against one another. This multi-pronged attack will reveal if the strength of dark energy has varied over the vast expanse of cosmic time. Any detected change, no matter how slight, would be a revolution. It would shatter the simple cosmological constant model and point toward a dynamic force like quintessence, a field that evolves and could potentially dictate a far more dramatic future for the cosmos. The data collected by these giants will either finally crack the code of the silent expansion or, as often happens in science, peel back the curtain to reveal an even deeper and more baffling mystery waiting in the dark. These digital universes run on some of the most powerful supercomputers on Earth. They are not simple animations but complex mathematical engines, known as n-body simulations, that choreograph the dance of billions of particles under the influence of gravity and cosmic expansion. Projects with names like the Millennium Simulation and Illustris TNG begin with a near-uniform sea of dark matter, the invisible scaffolding of the cosmos. Then they set the clock in motion, simulating billions of years of evolution in a matter of weeks. The laws of physics are programmed in, including the subtle, relentless push of dark energy. What emerges from this digital primordial soup is astonishingly familiar. Vast filaments of dark matter snake across the virtual void, drawing ordinary matter into their gravitational embrace. At the intersections of these filaments, galaxies ignite, spinning and colliding in a cosmic ballet that mirrors our own observable universe. These simulations are the ultimate testing ground. Scientists can run the same initial conditions over and over, tweaking a single variable each time. What happens if dark energy is a true constant, a steady pressure across all of time? They run the simulation and watch as a specific cosmic web unfolds. Then they change the rules. What if dark energy is a dynamic force like quintessence, growing stronger over the eons? They run the simulation again and observe a different universe take shape, one where galaxies might form earlier or later, where the vast voids between clusters grow at a different rate, or where the subtle lensing of light by dark matter creates a distinct pattern. By comparing these myriad virtual universes to the one we actually live in, cosmologists perform a kind of cosmic fingerprint analysis. They look at the real distribution of galaxy clusters, the precise geometry of the cosmic web, and the ways gravity bends light around massive objects. The simulation that leaves a fingerprint matching our reality tells us which version of dark energy is most likely to be true. This process places powerful constraints on the possible nature of this mysterious force, ruling out entire families of theories that fail to build a universe that looks like our own. Without these digital laboratories, the silent expansion would be an impenetrable mystery. They allow us to rewind and fast-forward the cosmos, testing the very laws of physics against the grandest experiment of all, the universe itself. The precise strength of dark energy feels almost too perfect. It is strong enough to push galaxies apart on the largest scales, yet so incredibly weak that it allowed the universe to cool and structure to form for billions of years before it took over. This delicate balance forces us to confront a deeply philosophical question, one that touches the very reason we are here to ask it. Why does our universe possess these specific properties, this exact recipe of physical constants, that allow for the existence of stars, planets, and conscious life? This line of reasoning is known as the Anthropic Principle. It suggests that the universe we observe must be compatible with the existence of observers. Think of it like this: you could not find a fish pondering why it lives in water, because a fish that evolved to live in water would, by necessity, only find itself in water. In the same way, we can only measure the laws of physics from within a universe that permits our form of life. Apply this to dark energy. If its repulsive force were just slightly stronger by a factor of perhaps 10, the universe would have blown itself apart in its first frantic moments. No galaxies would have condensed from the expanding gas, no stars would have ignited, and no planets could ever have formed. The cosmos would be a cold, dark, and empty void. On the other hand, if dark energy were significantly weaker or completely absent, gravity would have had a much stronger grip. The universe might have expanded only briefly before collapsing back in a catastrophic big crunch, a fiery end that would have come long before the first single-celled organism could stir. Our existence seems to hinge on a knife's edge, on a value for dark energy that is neither too strong nor too weak, but just right. This apparent fine-tuning presents a stark choice. Is it an astronomically lucky coincidence, a 1 in a trillion chance that we just happen to win? Or is there another explanation that removes the need for luck altogether? This is where the idea of the multiverse emerges, a concept as controversial as it is compelling. The multiverse theory proposes that our universe is not the only one. It is simply one bubble in a vast, perhaps infinite cosmic foam, a single page in an endless library. In each of these other universes, the fundamental constants could be radically different. In most, the conditions would be hopeless for life. Dark energy might be so powerful that those universes tear themselves apart in an instant, or so weak that they collapse immediately. But in a tiny, tiny fraction of these countless universes, the numbers by pure chance line up perfectly. We do not live in a special universe fine-tuned for us. We simply live in one of the rare universes capable of hosting us, a lonely oasis in a vast desert of uninhabitable realities. The multiverse is not a testable scientific theory in the traditional sense. We cannot build a telescope to see another bubble universe. But as a philosophical framework, it transforms the question of our existence. It suggests that the silent expansion and its curiously gentle push are not a puzzle to be solved, but a signature of our cosmic address, a quiet clue to a reality far grander and stranger than we ever imagined. This relentless expansion is quietly writing the final chapter of time itself. We all feel time's arrow flying in one direction, from a remembered past toward an uncertain future. This is not just a human experience, it is a fundamental law of the cosmos, dictated by the relentless rise of disorder known as entropy. The second law of thermodynamics is clear: in any isolated system, chaos always increases. The universe itself is the ultimate isolated system, and it began in a state of almost unimaginable order. Think of the Big Bang not as a chaotic explosion, but as an exquisitely concentrated, low-entropy seed. From that moment of perfect organization, the cosmos could only evolve in one way, toward greater and greater disorder. This is the journey to the heat death, the final state of uniform cold and darkness. But what keeps this journey on its one-way track? Dark energy is the silent engine of this cosmic decay. As it pushes the fabric of space apart, it creates an ever larger stage for chaos to play out. Imagine a small, crowded room where everyone is standing still. This is an ordered state with low entropy. Now, the walls of the room begin to fly outward, creating a vast, empty stadium. Suddenly, there is an enormous amount of space for people to move into, to mix and mingle in countless new configurations. The system has become vastly more disordered. This is precisely what dark energy does to our universe. With every moment of accelerated expansion, it creates more volume, more possible states for every particle of matter and energy to occupy. The drive toward maximum entropy is not just continuing, it is being turbocharged. The silent expansion ensures that the cosmic clock can never be wound backward. because there is no force powerful enough to gather all that dispersed energy back into a single, ordered point. In this profound sense, dark energy is more than a mysterious force pushing galaxies apart. It is the cosmic agent of time's arrow, the silent guarantor that the universe will move forever forward into its cold, dark, and final state of rest. The cosmos has a secret rhythm, a pulse of acceleration that has marked both its birth and its impending fate. Long before dark energy began its slow, steady push, the universe experienced another, far more violent growth spurt. In the very first sliver of a second after the Big Bang, a phenomenon known as cosmic inflation took hold. This was not the gentle expansion we see today, but an unimaginable burst where the fabric of space itself stretched faster than the speed of light, smoothing the cosmos to an incredible uniformity and planting the microscopic quantum seeds that would one day grow into galaxies. This event was driven by a completely different engine, a hypothetical field dubbed the inflaton. Its job was to jump-start the cosmos, and then it vanished, its work complete. Yet here we are, 14 billion years later, watching as a new form of acceleration, dark energy, takes over. The universe has now entered its second great age of acceleration. This cosmic echo is too striking to ignore. Could the inflaton field of the ancient past and the dark energy of the present be related? Some physicists wonder if they are different faces of the same fundamental force, a single actor playing two roles in the cosmic drama. Perhaps the same underlying physics that caused space to balloon in its first instant is also responsible for its silent, modern expansion. The mechanisms appear utterly different, one a transient firestorm and the other a persistent, gentle pressure, yet the outcome is the same. The fabric of reality is being stretched apart. Uncovering a potential link between them is one of the holy grails of theoretical cosmology. A unified theory that connects these two epochs would weave a single, continuous story from the universe's first trillionth of a second to its final, dark eons. It would give us a complete picture of cosmic destiny, showing how the same fundamental forces have guided the universe from its explosive beginning to its silent, expanding end. A profound misunderstanding about our expanding universe is that everything is flying apart. This is not the case. The silent expansion is not a force that tears planets from stars or shreds galaxies. It is a phenomenon that only dominates the vast, empty voids between the great cosmic structures. Within a galaxy like our own Milky Way, gravity has already won the local war. The solar system is held in a tight, stable dance by the sun's gravity, and the billions of stars within our galaxy are bound together by the immense gravitational pull of its central supermassive black hole and its own vast mass. This same principle applies to our local neighborhood of space. The Milky Way and the Andromeda Galaxy are not being pushed apart by dark energy. In fact, they are on a collision course, drawn together by their mutual gravitational attraction, destined to merge in billions of years. Even entire clusters of galaxies are gravitationally bound islands in the cosmic sea, their internal gravity far too strong for the subtle push of expansion to overcome. It is only in the immense dark deserts between these island clusters that the expansion becomes meaningful. There, in the near nothingness, the fabric of space itself can stretch unimpeded. Another common image is of dark energy as a cosmic wind, actively pushing on galaxies like a hand shoving a boat away from a dock. This, too, is a misleading picture. Dark energy is not an applied force. Think of it instead as a fundamental property of empty space, an inherent tendency for the vacuum itself to grow. As new space is created in the voids between unbound galaxy clusters, the distances between them increase. The galaxies are not moving through space away from each other. They are being carried apart by the stretching of the stage upon which they sit. It is the relentless addition of new space that creates the acceleration we observe. Clarifying these subtle points is essential. It shifts our view from a sensationalized cosmos tearing itself to pieces to a more nuanced and accurate reality, where local gravity creates islands of order, while on the grandest scales, a silent, inherent property of nothingness itself guides the ultimate fate of all we see. This search for a ghostly force is quietly building our technological future. While astronomers stare into the void, their tools are sparking revolutions right here on Earth. The drive to map dark energy has demanded entirely new classes of instruments, pushing engineering to its absolute limits. Consider the heart of a modern telescope, its digital camera. To capture the faint light from billions of galaxies, we needed to invent something extraordinary. The Vera-C Rubin Observatory, for instance, features the largest digital camera ever built for astronomy, a 3.2 gigapixel marvel. Developing its charge-coupled devices, or CCDs, required breakthroughs in ultra-pure silicon manufacturing and ultra-sensitive light detection. These are not just cameras for the stars. The same core technology now enhances medical imaging, allowing for lower-dose X-rays with higher resolution, and it refines the processes used to etch billions of transistors onto the tiny chips that power our phones and computers. The challenge does not end with capturing the light, but with understanding the flood of information it brings. A single night of observation at one of these mega telescopes can generate terabytes of data, a deluge that would be impossible for any human to sift through. This forced cosmologists to become pioneers in big data. They created sophisticated machine learning algorithms to automatically identify galaxies, classify star types, and find the subtle distortions caused by dark matter. These are not niche tools. The very same data processing techniques, born from the need to analyze the cosmos, are now used to detect fraudulent credit card transactions, predict disease outbreaks by analyzing global health patterns, and train the artificial intelligence that recommends your next movie. The quest to understand the universe's expansion has, in effect, built a powerful new toolkit for managing the information age. Beyond the hardware and software, this grand endeavor is forging a new kind of global community. Projects like the Rubin Observatory and the Euclid Space Telescope are not solo ventures. They are massive international collaborations, uniting thousands of scientists, engineers, and software developers from dozens of countries. This shared, fundamental goal transcends borders, fostering a rare and powerful spirit of cooperation. In the process, it trains a generation of problem solvers. Students and young researchers working on these projects gain unparalleled experience in data science, advanced computing, and systems engineering, skills they then carry into careers across the economy, from aerospace to finance. The silent expansion of the universe may feel like a distant, abstract puzzle, but our journey to solve it is weaving a tangible web of innovation, collaboration, and human capital that benefits us all, proving that the value of asking the biggest questions echoes far beyond the stars. The staggering price tag of cosmic discovery forces a difficult question. A single observatory designed to study dark energy can cost billions of dollars, a sum that could fund countless humanitarian projects here on Earth. When we face immediate crises like poverty, disease, and a changing climate, how can we justify spending so much to peer into the far future of the cosmos? This is not a question with an easy answer, but a profound ethical dilemma that sits at the heart of big science. The debate often pits immediate human needs against the long-term pursuit of pure knowledge. Critics rightly ask if such vast resources might be better directed toward building hospitals, developing clean water systems, or funding medical research. The suffering of the present feels infinitely more urgent than the silent expansion of the universe a billion years from now. Yet the scientists and engineers behind these projects offer a different perspective, one of long-term investment. They argue that the drive to understand our universe is a fundamental part of what makes us human. The inspiration a child feels seeing a new image from the James Webb Space Telescope is not a trivial thing. It can ignite a lifelong passion for science and problem-solving, creating the next generation of innovators who will tackle the very earthly problems we worry about. Furthermore, the technological challenges of building these cosmic observatories force breakthroughs that ripple through our entire society. The need for more sensitive sensors leads to better medical imaging equipment. The demand to process unimaginable amounts of data drives advancements in computing and artificial intelligence. These are not just happy accidents, they are direct results of aiming for the stars. The debate ultimately hinges on a delicate balance, a recognition that caring for our world and seeking to understand our place within the cosmos are not mutually exclusive goals. It underscores a crucial responsibility for the scientific community to clearly and passionately communicate the value of their work, not as an abstract luxury, but as a vital thread in the fabric of human progress, one that weaves together wonder, innovation, and a deeper understanding of our own planet. Massive telescopes and supercomputers do not hold a monopoly on cosmic discovery. The human eye and brain remain uniquely powerful tools in the quest to map the universe, and this is where anyone can join the hunt. Through online citizen science platforms like Zooniverse, the task of classifying galaxies from vast digital sky surveys is outsourced to a global army of volunteers. Spotting the subtle differences between a swirling spiral and a smooth elliptical galaxy is something our pattern recognition excels at, a challenge that still often stumps even the most sophisticated algorithms. Every click by a volunteer, a student, or a retiree with a curious mind contributes a vital data point, helping to build the immense, clean catalogs of galaxies that are essential for tracing the cosmic web and understanding how dark energy has shaped it over time. Beyond digital classification, amateur astronomers with backyard telescopes serve as the sentinels of the night sky. Their constant monitoring makes them exceptionally skilled at noticing when a new point of light appears where none was before, often providing the first alert of a supernova explosion in a distant galaxy. This early warning gives professional observatories precious time to swivel their massive instruments toward the new cosmic bomb, capturing its light curve in exquisite detail from the very beginning. This partnership between the public and professionals does more than just process data. It weaves a vital thread of connection between society and the stars. By democratizing discovery, it transforms abstract science into a shared human endeavor, building a foundation of public wonder and support that ensures our journey to understand the silent expansion can continue for generations to come. That same silent expansion, destined to end in cold darkness, holds a curious power over the human mind, confronting the sheer scale of the cosmos and the eerie reality of dark energy triggers a deep, emotional response that astronauts often describe as the overview effect. Seeing the Earth as a fragile, blue marble suspended in the black void fundamentally reshapes their perspective. For those of us with our feet firmly on the ground, learning about the universe's fate can produce a similar, profound shift. It is a feeling of awe, a breathtaking mixture of humility and wonder at our tiny place within an immense, unfolding story. This cosmic perspective has the power to shrink our daily anxieties and personal conflicts, rendering them almost trivial against the backdrop of billions of galaxies and trillions of years. Suddenly, the arguments and divisions that consume so much of our energy feel less significant. Instead, a deeper appreciation emerges for the only home we have ever known. Our planet transforms from just a place we live into a rare, vibrant oasis of life in a vast and mostly inhospitable cosmos. This awareness can be incredibly empowering. While the universe's long-term future may appear bleak, we are living during a spectacularly unique moment. We exist in a narrow window of cosmic time, after the first stars have forged the elements of life but before the last stars have flickered out. More importantly, we are the part of the universe that has become self-aware, capable of looking back and questioning its own origins and ultimate fate. The fact that we can observe distant supernova, map the cosmic microwave background, and ponder the mystery of dark energy is not a small thing. It is a staggering privilege. This knowledge does not have to lead to despair. Instead, it can fuel a renewed sense of purpose, driving creativity, scientific inquiry, and a collective responsibility to safeguard our fragile world and extend humanity's brief, precious chapter in the cosmic story. This silent force governing the fate of galaxies compels a profound conversation between two giants of physics that have never been able to agree. On one hand, you have Einstein's general relativity, a masterpiece that paints a beautiful picture of the cosmos on its grandest stage. It describes the smooth, geometric curvature of spacetime where planets orbit and galaxies dance. On the other hand, you have quantum mechanics, the rulebook for the frantic, probabilistic world of the atom. It governs the behavior of particles so small that certainty dissolves into a cloud of possibility. Both theories are spectacularly successful in their own domains, yet they are fundamentally, stubbornly incompatible. When you try to apply the equations of gravity to the quantum scale, or the rules of quantum weirdness to the heart of a black hole, the math simply breaks down, producing nonsensical infinities. Dark energy is the ultimate manifestation of this conflict. To truly understand why empty space exerts this repulsive push, we need a theory that can speak the language of both the cosmos and the quantum, a single framework known as quantum gravity. This is the holy grail of modern physics, a set of rules that can describe everything from the Big Bang to the behavior of the tiniest flicker of existence. The quest to explain the silent expansion is at its core a search for this final, unified theory of everything. Candidates for this monumental task are as mind-bending as the problem they seek to solve. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. Every particle, every force, is just a different note on this microscopic cosmic string. In this view, the fabric of spacetime itself is woven from these vibrations. Another compelling idea, loop quantum gravity, suggests that space is not smooth and continuous, but is actually composed of a network of finite, woven loops, a kind of atomic fabric of reality. At the tiniest possible scale, the Planck length, spacetime may be a seething, granular foam. This is a distance so small that 1 trillion of these grains could fit across a single proton. The properties of this fundamental structure, whether it is made of strings or loops, could be the ultimate source of the vacuum energy we call dark energy. The gentle pressure pushing the universe apart may be the collective sigh of a quadrillion tiny, quantum grains of spacetime, each one vibrating with an energy that echoes across the cosmos. This means the ultimate fate of every star and galaxy is inextricably tied to the physics of the very small, a connection that bridges the vastest emptiness with the most fundamental building blocks of reality. The silent expansion of our universe is the ultimate cosmic whisper, a profound discovery that has rewritten our place in the cosmos. From the initial shock of distant supernova to the frozen echoes of the Big Bang, every line of evidence points to a reality dominated by a mysterious force we cannot see. We have traced the leading theories, from Einstein's resurrected constant to the dynamic possibilities of quintessence, and confronted the stark futures of a cold big freeze or a violent big rip. This journey is far more than an academic puzzle. It represents a fundamental human quest to understand the fabric of reality itself, pushing the very limits of our knowledge and technology. While countless questions remain unanswered, our relentless pursuit embodies the very best of human curiosity and ingenuity. The cosmos is communicating with us through this silent, accelerating expansion. We have only just begun to learn its language. What profound new mysteries will the next generation of telescopes reveal as they stare deeper into the dark?